This is 12.7 Part 3, and we'll now look at some applications of the directional derivative. We'll actually look at a couple that are quite similar, but one two-dimensional and the other one three-dimensional. In example 4, we're told that suppose that we have a single heat source. The temperature at any point will be inversely related to the distance from the heat source. Makes sense, right? The further away you go, the lower the temperature. So here's our temperature function, 100 over 5 plus x squared plus y squared. Notice that if you're right at 0, 0, that's going to be the largest possible value of t, and the bigger the values of x and y, the smaller the fraction gets, the lower the temperature gets. Right now we have an ant at the point 36. And my first question is just what's the current temperature? So that's just the temperature at the point 36. Just a matter of plugging into our given function. And let's see, that looks like a calculator problem to me. Actually, I probably could have done that one in my head. It came out to 2, nice and evenly. I just didn't notice. I think later on I said to measure degrees Celsius as our temperature, so we'll go with 2 degrees Celsius here. All right, for part B, we'd like to know if the ant crawls in the direction 2, 3, what is the rate of change of temperature? Now, as soon as I'm asked for the rate of change, I know I'm being asked for a derivative. And since I'm going in kind of a random direction, not parallel to either the x or the y-axis, I know I'm going to want a directional derivative. Okay, so rate of change still signals derivative, just like it always has. It's just the randomized direction that tells me it's a directional derivative. All right, so I need a gradient and a unit vector to calculate that directional derivative. Let's start by getting the gradient. Gradient of t would be t sub x, t sub y. And I'm going to think of this as 100 times 5 plus x squared plus y squared to the negative 1, just to make my derivatives a little easier. So t sub x, negative 100 times 5 plus x squared plus y squared to the negative 2 times 2x for the chain rule. And then t sub y, very similar. But my chain rule will give me 2y. So I end up with negative 200x over 5 plus x squared plus y squared all squared. And then negative 200y over the same thing. Since we're going to start at the point 36, let's go ahead and plug in that x and y value. I'd have negative 200 times 3 over 5 plus 3 squared plus 6 squared squared. And negative 200 times 6 times the same over the same thing. And I'm just going to go ahead and do the arithmetic on the calculator to make it a little faster. And I ended up with a negative 0.24 for the x component and negative 0.48 for the y component. So there's my gradient vector. I also need a unit vector in the direction of motion. So in this case, we wanted to go in the direction 2, 3. So I just had to turn that into a unit vector. Looks like I'll get 2 over the square root of 13 3 over the square root of 13. And that means my directional derivative, the derivative of t in the direction of u, is just the dot product of the two things I just found, the gradient and the unit vector. And I'm just going to go with a decimal approximation here. I'm just going to, again, do this on my calculator. So let's see, when I take the product here, I got about negative 0.133. And when I took the product here, I got about negative 0.399. Giving me a final directional derivative of about negative 0.53. So what's that telling us? Well, it's telling us that we started, remember, with a temperature of 2 degrees, and when the ant is crawling in the direction of the vector 2, 3, it's experiencing a temperature decrease of 0.53 degrees per unit or per meter that it travels. So, again, the ant experiences a temperature decrease, since we got a negative directional derivative, of 0.53 degrees Celsius per meter that it travels. Now again, remember this is an instantaneous rate of change, just like all derivatives are. So as soon as it moves a little bit, the rate of change of temperature will also change. All right, for part C, we've actually done most of the difficult work. We still start at the 0.36, meaning that our gradient vector won't change. The only difference is the direction that we want this ant to move. So we want it to go in the direction 1, negative 4. So my unit vector, positive 1, negative 4. Will be 1 over the square root of 17, negative 4 over the square root of 17. And that means that our rate of change, or directional derivative, is just the dot product of those two vectors. And again, I'm just going to do that on the calculator to get a decimal approximation here. Multiplying those together, I got about negative 0.058. And multiplying these guys, I got about 0.466. And adding those together gives me a directional derivative of about 0.408, or about 0.41 if I round to 2 decimal places. So this time, as the ant crawls, it's warming up at the rate of 0.4 degrees or 0.41 degrees Celsius per meter. I want to take just a really quick look at the geometry of this problem, because I think the cooling down here and the warming up there should make sense if we think about this. Remember that we had a heat source right at the origin, right? So here's my heat source. This ant is at the point 36. So it's right there. And the first problem said that it crawled in the direction 2, 3. So it went over 2 and up 3. Meaning it went this way, in the direction of the vector 2, 3. Definitely the ant is getting further away from the heat source, so the fact that we ended up with a decrease in temperature made sense. What about the second part? The ant was going in the direction 1, negative 4. So it was going over 1, but down 4. Notice in this case, it's getting closer to the heat source. And so it would make sense that the temperature would be warming up. We got a positive rate of change. That's logical for that problem. All right. Example 5 is actually quite a similar problem. It's just an example in 3 dimensions, a little bit more algebraically heavy. So you can decide whether, I'm going to go through it. You can decide whether you want to follow through or say, hey, I got it. That's up to you. But I'm going to go ahead and go through this one. In this case, instead of crawling around an ant in a plane, we have a 3-dimensional situation where a bird is flying around. So it has a 3-dimensional location, and it can travel in the direction of a 3-dimensional vector. Here's my temperature function. Notice same idea, the heat source is at the origin. At 0, 0, 0, the temperature would be 50, that's as large as it can be. And the larger the x and the y and the z become, the smaller the value of the overall fraction. The temperature gets cooler. Current temperature. Let's see, we were at the point -2, 4, 2. So if I plug that into my t function, see, x squared would be 4, y squared 16, z squared 4. That is the square root of 25 or 5. 50 over 5 would be 10. I'm going to assume the same units, so I'm going to say, currently, that bird is experiencing a temperature of 10 degrees Celsius. In parts B and C, we're asked for rates of change in arbitrary directions. So we know in both cases here we're going to want a directional derivative. And in order to get a directional derivative, I definitely need a gradient vector, which is somewhat unfortunate. This is not a very pretty function, but we'll get it, right? So let me start part B out by looking for my directional derivative. Or excuse me, by looking for my gradient function. T sub x, T sub y, T sub z. Again, I'm going to use sort of the same cheat as last time. I'm going to think of this as 1 plus x squared plus y squared plus z squared to the -1/2 power, making it a little bit easier to differentiate. So my derivative is going to be -1/2 times 50 would be -25 times all of this to the -3/2 times 2x for the chain rule. And I'll get exactly the same thing for the y and z derivatives with the exception of the chain rule piece, right? So let me just jot those down. This one will be times 2y. And the last one will be times 2z. In both parts B and C, we're still starting at the point -2, 4, 2. So I might as well go ahead and calculate that gradient at that point. So let's see what we're going to get here. We are going to get -50 times -2. I'm going to put this in the bottom. 1 plus 4 plus 16 plus 4 to the 3/2 power. Here I would have, oops, here, -50 times the y, so -50 times 4 over the same thing. And here again I'll have a -50 times the z value, which is 2, over that same denominator. All right, and again, this denominator, we already knew that that was 25 in there. So square root of 25 is 5, and 5 cubed would be 125. So I have 100 over 125, negative 200 over 125, and negative 100 over 125. Reducing that is going to give me 4/5, negative 8/5, and negative 4/5. Let's say it, I just can't write it. There we go. All right, unit vector. In the first part, part B here, we wanted to move in the direction of 3, 1, negative 1. So I'll turn that into a unit vector. Looks like 3 over the square root of 11, 1 over the square root of 11, and negative 1 over the square root of 11. And so my directional derivative is that gradient vector that we calculated, dot product with our unit vector. And let's see, that's going to be 12 over 5 square root 11. Actually, all the denominators are 5 square root 11, so I'm going to put it all in one big fraction here. Negative 8 over the same thing, and positive 4 over the same thing. So I end up getting 8 over 5 square root 11. Okay, last one I gave a decimal approximation. This one I'm giving exact. You can do it either way, unless the directions say one way or the other. It's your choice. All right, part C, same problem. The only difference is the direction. We would like to fly now in the direction negative 3, 0, negative 4. So the gradient vector won't change, but the unit vector has to be in the direction of negative 3, 0, negative 4. Denominator is the square root of 25, or 5. So negative 3/5, 0, negative 4/5 is my new unit vector. And my directional derivative, again, the gradient didn't change because I'm still starting at the same point. And I'll multiply that by my new unit vector. So I'm going to get negative 12/5 plus 0 plus 16/5, or 4/5 on that one. So in this particular case, it looks like we were actually getting warmer in both situations. All right, so there's a couple of applications of the directional derivative to the idea of rate of change. I'm going to do one last video for this section, and we will talk about the gradient itself and what it tells us.